Okay, hi guys, good morning. This is my second attempt at making this video. I did not like the first one, so I'm going to try and redo this video and hopefully help you with inverse trig functions. You might want to watch today's video and Tuesday's video before you do any of the homework because they kind of go together. So I'm splitting them up into two videos. This video will be about the analytical parts. And what I mean by that is that will be like simplifying expressions or solving equations or whatever. So that'll be the inverse function use in those things, expressions, equations. And then the part 2 video will be about the graphs. I tried to do both of them together and it made a really crappy video. So I'm going to do it over. So we are going to focus on inverse trig functions analytically first today. Focus on expressions and equations and what we've done with those before. And then the second video, which will be posted in tomorrow's checklist, which you might want to watch before you do the homework, we'll focus on the graphs. Okay, let's get going. So if you remember doing inverse trig functions with equations, this is our experience with an inverse trig function. Suppose somebody wants to solve the equation sine of theta equals 4/5. Okay? And what we need to do is we need to get the theta free. It's trapped inside the sine function. Now, if you remember, when things were trapped inside an x squared, we would take the square root of both sides. Or if it was trapped inside a cube root, then we would cube both sides. And those are inverse functions, squares and square roots, cubes and cube roots. Also, if we had like 2 to the x equals 4, then we would take the log base 2 of both sides. All right, so x would be the log base 2 of 4. All right, and so those are kind of the experiences we have with inverse functions. So we do the same thing, and the inverse function of sine is inverse sine. Or if you wish, it's, and we write it like this, inverse sine, or we write arc sine. And I don't care which one you use. I use this one all the time, so that's what I'll use. All right? So the inverse sine, we take the inverse sine of both sides to solve this problem. It's like taking the square root of both sides. So the inverse sine undoes the sine, and we get theta equals the inverse sine of 4/5. Now, this is an exact answer. It is correct. Typically, though, you will see it converted on a calculator. Now, my calculator is in radians, and so if I calculate this, I'm going to do the inverse sine of 4 divided by 5, 4/5. And I am going to get 0.9273 radians. Okay, now that's an approximate answer. Now, just so you know, you can do this in degrees as well, depending on the problem. And so you can do it in degrees, and you would get approximately 53.13 degrees. Okay? And so checking your mode, depending what the problem is asking for and the situation. But in general, we almost always do these in radians. But pay attention to what the problem is asking for. And this is how we solve. So if I had like a secant theta, then I'd take the inverse secant of both sides. If I had a cosine theta, I'd take the inverse cosine of both sides, etc., etc. This is what we know about inverse functions so far. We know that they undo each other to help us solve equations, all right? So what we want to do is we want to define these inverse functions a little bit more so we can use them to do more extensive problems, kind of see what's going on a little better. So one of the issues that will pop up and that you need to be aware of is for these inverse functions, we really need to pay attention to their domain and range. And so what I want to talk about is I want to talk about their domain and range a little bit. And so to do that, I just want to look at the graphs of sine, cosine, and tangent. So here's quickly the graph of sine. If you remember, it would look like this. And it would go on forever in that pattern. And the graph of cosine would look like this. And it would go on forever. And the graph of tangent would look like this. So this is what you got from the last lesson. And so tangent has asymptotes, and it kind of looks sort of like an x cubed function between the asymptotes. All right? Now, the problem with every one of these graphs, they all fail the horizontal line test, right? Every one of them every horizontal line will intersect them in an infinite number of points. And so what that means is we need to restrict the domain, okay? We need to restrict the domains of sine, cosine, and tangent so we can do the inverses. Now, just so you can remember this, if you'll remember when we had x squared, it also failed the horizontal line test, so it was not one-to-one, just like these functions, but then we restricted the domain to only the right half, and it would have an inverse function called the square root of x, all right? And if we restricted the domain to just the left half, it would have an inverse function called the opposite of the square root of x, okay? And so that's what's going to happen here. We're going to restrict domains. And just so you know, I'm going to draw in the restrictions here. The restriction on sine is going to go from here to here. Okay? The restriction on cosine is going to go from there to there. Okay? And the restriction on tangent, we're going to restrict ourselves to just this part. So when we define these functions and we look at them, these are the restrictions we're going to be looking at. Okay? Alrighty, so let's do that. So let's look at the inverse sine of x really quick. First of all, if y equals sine of x, here's our domain restriction right there. This is our domain restriction right here. X is an element, negative pi over 2 to pi over 2. And then the range, the y values, you can see that the y's will be an element of negative 1 to 1. All right, and these are closed intervals. All right, and so you'll go from negative 1 on the y to 1 on the y, and the x's go from negative pi over 2 to pi over 2. Anything after that becomes not a one-to-one function, because then a horizontal line will intersect it twice. If you just creep down just a little, you get a horizontal line hitting it twice. So we restrict that domain. So what's that mean about y equals inverse sine of x? And we're going to talk about these graphs a little bit more tomorrow. But what it means is that the domain of the inverse sine of x is x values from -1 to 1. All right? And the range, the y values, are from -pi/2 to pi/2. Okay? Now, we'll focus on the graph of inverse sine x in part 2 of this video, but I want to list this domain and range because this is really important. A couple of things happening here. When you take y equals sine x, the x, this is an angle. You take the sine of angles, okay? And you get a ratio. That ratio is always between 1 and -1. So when you do the inverse sine, this is the inverse sine of a ratio. And you always get for an answer an angle, okay? So when you do the inverse sine of things, the angle you get, could be listed in radians or degrees. So you want to pay attention to this issue, okay? So that's a really important thing to know, all right? And this comes from the fact that if you graph xy for a function, then if you remember, then yx will be on the inverse function, okay? So for instance, if somebody comes up to you and they say, oh, this point is on this function, so a typical point, an angle, I could say pi/3 and square root of 3/2. That's on the sine graph, okay? So what's on the inverse sine graph? Well, on the inverse sine graph, it'll be square root of 3/2, comma, pi/3. All right? Now, the other issue with inverse sine, and this is where we're going to start to talk about evaluating expressions, okay? That contain both an inverse function and a trig function, okay? An inverse trig and a trig, or more than one of those. When you start to evaluate those expressions, keeping in mind this idea about the angle and ratio is really important. And the reason it's important is once you do a trig function of an angle, you get a ratio, okay? Now, you can't take the trig of a ratio, so you could never say something like, find the sine of cosine 22 degrees. It doesn't make sense because then you're taking the sine of a ratio, and a ratio is not an angle. So this never makes sense. However, you could do something like find the inverse sine of cosine of 22 degrees. Because here's an angle. When you take the trig function, it's a ratio. And then you can take the inverse trig of a ratio, and that'll take you back to an angle. Okay? And so these are the kinds of expressions we're going to work with. So let's go to the next slide and start to look at that. So where this comes up is you are looking at this sort of expression, f inverse of f of x. If you'll remember, if two functions are inverse, then f inverse of f of x is equal to x. And also f of f inverse of x is equal to x. And so, in other words, the inverse of a function takes us back to the starting point. But the way this works with inverse trig is it doesn't take us back to the starting point all the time, but it does take us back to the same reference angle, all right, or to the same ratio, depending on how we've written it, all right? It could take us back to the same reference angle or to the same ratio. But that does not mean that the x value you start with in here is going to be the x value you have out here. And that has to do with how these domains intersect and overlap each other. All right? So one more domain comment, and then we're going to work on these problems. If you noticed on the earlier graph, the inverse sine of x, its domain is -1 to 1, but its range, the answer you get out after you take the inverse sine of an expression, is always -pi/2 to pi/2, all right? However, if you go to inverse cosine, all right, its domain is also -1 to 1, all right? But its range is 0 to pi. Now, if you don't remember this, go back and look at the graph back on slide 2 where I showed you where the inverse cosine graph was. Its range is from 0 to pi. So its range are first and second quadrant angles, whereas the inverse sine are fourth and first quadrant angles, okay? The positive ones are in the first quadrant, the negative ones are in the fourth quadrant, and you're going in the negative direction. But notice the reference angles will match up, all right? And then just for kicks, just for the last one, y equals inverse tangent of x. Its domain will be -infinity to infinity, but its range will also be -pi/2 to pi/2. Okay? And so if we start doing these problems, we've got to really pay attention to some issues that occur here. Now, just so you know, secant will be like cosine, cosecant will be like sine, and cotangent will, I believe, act like tangent. Yeah, inverse cotangent. All right? And just keep that in mind. Okay, let's look at a few problems. So what we can do now is we can write the definitions. So y equals the inverse sine of x means x equals sine of y, okay, with the domain equal to -1 to 1 and the range equal to -pi/2 to pi/2. All right? And then we can do the same thing for inverse cosine, inverse tangent. So y equals the inverse cosine of x means x equals cosine y. All right? With a domain from -1 to 1 and a range from 0 to pi. All right? And then y equals inverse tangent of x means x equals tangent y. And the domain is -infinity to infinity, and the range is -pi/2 to pi/2. So the first thing we can do is we can just start to practice writing things. So for instance, suppose I say the sine of 5 pi over 12, and I punch it out on my calculator, and it's approximately 0.96593. Okay? Then I want to be able to write an equivalent inverse sine expression, an equivalent expression. So that would be 5 pi over 12 is equal to the inverse sine of 0.96593. Okay, this is very much like writing if, 4 squared equals 16, then the square root of 16 equals 4. That's kind of what you're doing. You're writing the relationship and the inverse relationship, and they're equivalent expressions. Okay? Now, the next thing you want to do is you want to be able to evaluate inverse trig expressions for special angles and their ratios. So if we look at the table again, so sine, cosine, tangent, 0, pi over 6, pi over 4, pi over 3, pi over 2, and notice I'm just showing you can write this. So 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. So we write them in reverse for cosine because they're cofunctions. Oops, square root of 2 over 2, 1/2, and 0. And then we take the fraction. Okay, so if we have this table, which is just the first quadrant, this can really help us. So if we write an expression, so here's an example of an expression. So suppose I want the inverse sine of negative square root of 2 over 2, right? Okay. So if I look, here's sine, and here's pi over 4, there's square root of 2 over 2, okay? Now, notice I want the inverse sine of negative square root of 2 over 2. So I'm thinking about the range, okay? And if you'll remember, from 0 to pi over 2 is quadrant 1, but those are all positive. But 0 to negative pi over 2, those are quadrant 4 angles, and they're all negative ratios. So I want the quadrant 4 angle that will give me negative square root of 2 over 2. Or in other words, this is equal to y. In other words, I want the sine of y to equal negative square root of 2 over 2. Right? So what angle do I want from the fourth quadrant? Going clockwise, which means it's a negative angle. Well, that will be the sine of negative pi over 4 will give me negative square root of 2 over 2. So the answer here is y equals negative pi over 4. Okay? And that's how we're doing these problems. So we're gonna keep doing that. So I'm gonna shrink this a little, and we're gonna do a few more problems. Okay? All right. What if we want to find the inverse tangent of negative 1? Okay? The inverse tangent of negative 1. All right? And that's equal to some value, and I want to know what that is. Well, tangent of pi over 4 is 1. And again, the domain in this case is just like sine, so it's quadrant 1 and quadrant 4. So I want the quadrant 4 angle, which is -1, that I can take the tangent of, right? And so that's going to be -pi/4 is equal to y. Okay? Quadrant 4 angle, and that's how it works. Now, you can punch this on your calculator and check it. All right? So don't forget, you can do a calculator check. All right? But make sure you work on the thinking. It's the thinking that's important here. You need to think inverse function. So you need to do it the way I'm doing it and then check it on your calculator. Okay? Now remember, your calculator will give you a decimal. If you just punch in the inverse tangent of -1, you're going to get a decimal. So then you have to take -pi divided by 4 and see if you get the same decimal. And that'll tell you if you're doing it correctly. Okay? All right, let's do another one. Next one, let's do the cosine inverse of -1/2. All right? So that's equal to y. So in other words, I want the angle, right, that will give me -1/2. But for cosine, the first quadrant is positive, so first quadrant angles are positive, but we need second quadrant angles to get negative values. And so from the table, the cosine of pi/3 is 1/2. So the second quadrant angle of pi/3 is 2 pi/3. So y is equal to 2 pi/3. Now I did the negatives in every case here just so you could see that. So this is your process. Now, you can do this process with random radians, okay, as well. So I'm going to shrink it a little more. We still have all our work here. All right. So I could do it with a random radian. Suppose somebody comes up to me and they say, okay, what is the inverse cosine of 1 equal to? Okay. What's the inverse cosine of 1 equal to? All right. Well, just like I thought before, it's the cosine of some angle that will give you a ratio of 1. All right. Now, if it's not a special angle value from the table right here, you could find this just by using a calculator. All right. So I would go inverse cosine of 1 and put myself in radian mode, all right, because the ratio is 1, and the inverse cosine of 1 is, hang on a sec, sorry, punching my calculator. The inverse cosine of 1 is just 0. Oh, but notice that's a special. I didn't mean to choose 1. I meant to do something like 1.4. So then we can do the inverse cosine of 1.4. Okay? Oh, and that was a bad issue because remember, the ratios can't be greater than 1. So sometimes you'll get problems like this and you'll do it on a calculator. And the cosine of anything, this gets at the domain issue of cosine up here between -1 and 1. So I just went on and messed up a whole problem there. So you'd have to see something like the inverse cosine of 0.9, where the value was between. But if they just give you a number between -1 and 1 as a decimal, and it's not a special angle, then you can use a calculator, okay? Sorry about that. It's good to make mistakes. So this would be 0.45 radians is equal to y. So this would be the angle, okay? All right, next slide. So now we start to get into some interesting problems. And this is that f inverse of f equals x. And normally we would think, well, a square root undoes a square. So doesn't an inverse sine undo a sine? And is the answer just 3 pi over 4? All right. And we could check this. We could punch this all in a calculator, okay? So I can go the inverse sine of 3 pi divided by 4. And it'll give me an answer, all right? I just punch it on my calculator. 0.7854, okay? And then I say, okay, 3 pi over 4, what is that? So 3 times pi divided by 4. Wait a second, that's 2.3561 or 62. So the ratios are not the same. And I go, ooh, questions arise in my head. So these are not just calculator problems here. These become thinking about the issues that you come across with inverse functions, okay? So here's how you do this problem. You, especially when there are exact angles listed or ratios from the exact angle table, you want to go through these and make sure you understand them. So what we do is, first of all, we ask ourselves, what's the sine of 3 pi over 4? This is sort of our first step. The sine of 3 pi over 4, according to my unit circle or my table, this is a second quadrant angle, and the sine of 3 pi over 4 is positive square root of 2 over 2, okay? So that means the inverse sine of the sine of 3 pi over 4 is equal to the inverse sine of the square root of 2 over 2. Now remember, when you take the inverse sine of an expression, it has to be a first or a fourth quadrant angle. This is positive, so we want the first quadrant angle that gives us the ratio square root of 2 over 2. And that is going to be pi over 4. And so right away on this first problem we do, you see that you need to do this step by step versus just assuming things undo each other. And this is a big deal, okay? So let's go to another problem. Next problem, okay? Let's try inverse cosine of 2 pi over 3. Now, the cosine of 2 pi over 3 is equal to -1/2. Because the cosine of pi over 3, cosine of pi over 3 is 1/2. But 2 pi over 3 is a second quadrant angle, so the cosine of 2 pi over 3 is -1/2. So we get -1/2 here. Now the inverse cosine of a -1/2, its range is 0 to pi. So we want the second quadrant angle because this is negative. So it's just going to give us 2 pi over 3. So it turns out the inverse cosine of cosine is going to work out like you expect. They're just going to undo each other. But the inverse sine and the inverse tangent are not going to do that. because any angles outside the first or the fourth quadrant aren't going to get undone. You have to work back to the corresponding angle that has the same reference angle. And the inverse cosine, this happens. What if I had changed the problem and I went the inverse cosine of 4 pi over 3? Okay, well now 4 pi over 3 is a third quadrant angle. All right, now cosine's negative there, so this is still negative 1/2. All right, but the inverse cosine of negative 1/2 takes us back to a second quadrant angle, to 2 pi over 3. So see, the same thing can happen on the inverse cosines that happen on this inverse sine problem. You have to pay attention where the domain and the range are. So this tells us that when we're given functions or when we're given new functions, we need to really know what the domains are. Okay? All right, let me see if there's any other problems I like here. Okay? Oh, here's a good one. So here's one with an angle that's not obvious, all right? So let's go with the inverse tangent of pi over, or of the tangent of pi over 8, okay? Now, pi over 8 is not a special angle, okay? However, what we do know about pi over 8 is that it's in the first quadrant, right? It's even less than pi over 6, right? It's going to be somewhat less than that. So it's a first quadrant angle. So since it's a first quadrant angle, the tangent of that will be a positive ratio, and the inverse tangent of that will take us directly back to pi over 8. Okay? All right, so keep that in mind. So now let's go to the next one. Suppose we do the inverse tangent of the tangent of 11 pi over 9. Okay? Now, where is 11 pi over 9? Well, 9 pi over 9 is equal to pi, so 11 pi over 9 is in the third quadrant. Okay? Since pi is here, which is 9 pi over 9. 11 pi over 9 is in the third quadrant. So you have to figure out what quadrant it's in. Okay? So that's the third quadrant. But remember, our answers are going to be first or fourth quadrant angles. All right? Positive, negative. Now, tangent of 11 pi over 9 is positive in the third quadrant. Okay? So we want the angle that has the same reference angle as 11 pi over 9, but it's in the first quadrant. Well, you can just draw that straight across, and that'll be 2 pi over 9. All right? Got it? 11 pi over 9 minus pi is 2 pi over 9. That's the reference angle. So now you see how important reference angles are. So tangent of 11 pi over 9 is positive. It's a third quadrant angle. It's positive. But the inverse tangent of a positive ratio will be the first quadrant angle. So our answer is 2 pi over 9. Okay? I'll let you think about that. That's my favorite problem of the day. All right? I'm looking. Let's do another composition of functions here. What if, could we actually mix things up? So could we do like the inverse sine of the cosine of 13 pi over 6? So where is 13 pi over 6? So the first thing I want to know is where is 13 pi over 6? So if you notice, 12 pi over 6, that's 2 pi. So this is fully one rotation around, and it's in the first quadrant, 13 pi over 6. Okay? Reference angle is pi over 6. All right? So the cosine of 13 pi over 6 is the same as the cosine of pi over 6, because it's a special angle, right? And the cosine of pi over 6 is just square root of 3 over 2. And so the inverse sine of the square root of 3 over 2, since this is a positive ratio, that means we want the first quadrant. So the inverse sine of that is pi over 3. And there's your solution. Okay? Shall we do a couple of others? A couple of others, just for fun. Yeah, let's do another one. Let's do inverse cosine of sine pi over 3. How about that? So inverse cosine of sine pi over 3. All right. So again, we're going to proceed like we did last time. The sine of pi over 3, we know what that is. That's the square root of 3 over 1, or 2, excuse me. Square root of 3 over 2. And then I want the inverse cosine of a positive ratio. That means I want a first quadrant angle that will give me square root of 3 over 2. Cosine of that angle will give me square root of 3 over 2. And that is pi over 6. Okay? All right, evaluating expressions. Okay, so now let's go to ones where they switch things up on us. And these are going to show up on later problems. You will notice every problem we did here, as we worked through, we always had the inverse trig and then the trig of an angle. Okay? So now we're going to do that backwards. We're going to do something different. So it's going to look like this. We want to take the sine of the inverse cosine of 4/5. Okay? So now we're going to take the trig of the inverse trig. So that means this inverse trig is an angle, and we want to figure out what that angle is. And then we want to take the sine of that angle. Now, you can punch this in a calculator and get an answer, but that doesn't really teach you how to do the trig. And so do not punch this on a calculator except to check. So the way you want to do this problem is, you notice the inverse cosine is of a ratio. So whatever is inside an inverse trig function is a ratio. So this is a ratio, okay? Since it's a ratio, we can draw the triangle. And since it's a positive ratio, we can draw the triangle in the first quadrant, okay? So here's an angle, okay? And the ratio is inverse cosine, which means adjacent over hypotenuse. So this is 5, this is 4. And by the Pythagorean theorem, 4 squared plus y squared equals 5 squared, we can get y is equal to 3. All right? So remember, the inverse cosine of the ratio is an angle, right? So we basically want to know the sine of the angle. This angle here is the inverse cosine of 4/5. All right? So we basically want to know the sine of that angle, and the sine is opposite over hypotenuse. So it's 3/5. Now, let's go over the steps to this problem again. We have a trig function of an inverse trig function. The inverse trig function is an angle, but the inside part of it is a ratio, okay? Given whether that ratio is positive or negative, and whether our inverse cosine or inverse tangent or whatever, that's going to tell us what quadrant our triangle is in, okay? Since it was positive, it's quadrant 1. I can set up that triangle, use the Pythagorean theorem to find the other side, and then I just am asking, what is the trig function of this angle? Well, that angle was this expression. So the trig function of that angle, in this case, is opposite over hypotenuse 3/5. Okay? And this is something we do all the time. So let's go do a couple of others. Let's do this one right here. Let's do the cosine of the inverse tangent of negative 5/12. Okay? So, this is a negative 5/12. If you remember, the range of inverse tangent was negative pi over 2 to pi over 2, and the negative ones were in the fourth quadrant. So this triangle is a fourth quadrant triangle. Okay? Here's our angle. Remember, that angle is the inverse tangent. Now here's our ratio. Negative 5/12. The hypotenuse is 12. All right? Or excuse me, the adjacent is 12. And the opposite is 5. Because tangent is opposite over adjacent. All right? Now notice, this is a negative 5 on the y. So we do our Pythagorean theorem. So we get to find the hypotenuse. 5 squared plus 12 squared equals hypotenuse squared. So 25 plus 144 equals h squared. So 169 equals h squared. So we get 13 is the hypotenuse. All right. Now we want to find the cosine of this angle. And this is our angle. The whole thing's the angle. All right. We use the ratio part to set up the triangle. Okay. And cosine is adjacent over hypotenuse. So the adjacent is 12. It's going to be 12/13. Because cosine is positive in the fourth quadrant. Okay? Starting to like these? These are some of my favorite problems ever. So let's do one more. Let's do a variable kind of problem. A variable kind of problem. All right, last one. What if you had the sine of the inverse tangent of 4x? All right. And they tell us, whoops, let me rewrite it here. The sine of the inverse tangent of 4x. I accidentally hit the thing. And they tell us x is between negative 1/4 and 1/4. So now they're giving us a range on the x. All right. Okay. So we're going to do the same thing. This gives us a ratio. All right. When the x is positive up to 1/4, right, it's first quadrant. When it's negative, it's a fourth quadrant. So what we're looking at here is we could have this triangle here or the same triangle here. All right. Now tangent is opposite over adjacent. So this is 4x and this is 1. And in the same way, this is 4x here when the x happens to be negative. Okay? Here's our angle. So, by the Pythagorean theorem, we get 4x quantity squared plus 1 squared equals the hypotenuse squared. So we end up with 16x squared plus 1 equals the hypotenuse squared. So we get the square root of 16x squared plus 1 equals the hypotenuse. Okay? And I only get the positive one because I am referring to the hypotenuse. And it doesn't matter which triangle I'm using, I still get the same hypotenuse length. So I want the sine, which is opposite over hypotenuse, right? So here's my hypotenuse. So it's the square root of 16x squared plus 1. And the opposite is going to be the 4x. And it will be positive if the x is bigger than 0, but negative if the x is less than 0. So we get 4x over that. And this is our solution. All right? All those problems can be done the same way. So lots and lots of issues here. Now, if you want to look at this and see this a little bit more, it turns out that our website, Lumen Learning, you remember our old website, Lumen Learning? You can go to lumenlearning.com and search for inverse trig functions. Inverse trig functions on that at lumenlearning.com. And it kind of runs through this again and have some good examples. And this is our first video. Alrighty, bye-bye.